Hi everyone, this is another differential equations lecture. Today we are going to do a little bit of section 2.4 and mostly section 2.6 exact equation. From section 2.4 I want to point on uniqueness and existence theorem. As you probably remember, in section 2.1 we got a formula for solving differential equation which was looking like this: dy dt plus p of t y equals g of t. Remember, we considered linear equation looking like this, and we found that if you use integrating factor mu of t, which is equal e to the power of p of t dt, right, and then solution can be represented as integral that's just a book formula. So, well, what does it mean for us? For us, it means that basically, if equation looks like this and functions are integrable, for example, you can find integral of p of t dt. And remember that not very hard conditions on p and t to find the integral, right? Supposed to be, the function supposed to be continuous or piecewise continuous or just integrable, means that you can find area under it. And if you can find the area under the product, which means that you just need to have this continuous, which is going to be continuous if this one is continuous, exponential function is continuous, and if g of s is continuous. So basically, if p and g are continuous, there is always going to be solution looking like this. Well, you probably won't be able to find it as a formula, but solution will be looking like this, and you can use the computer and just calculate it numerically, but that's going to be a unique existing solution. Well, in the book, in section 2.4, we do have existence and uniqueness theorem for the equation of the first order. And it sounds like this. Theorem. Sounds like this. If p of t and, g of t are continuous on interval I for t between a and b, including, the interval is supposed to be include point t0, which is point where initial conditions are defined, then there exists, that's not my app, exists a unique function phi of t that satisfies the differential equation y prime plus p of t y equals g of t for each t in interval I and initial condition y of t0 equals y0, where y0 is arbitrary initial condition placed on interval. Okay, so remember how we were kind of using it, right? For example, if you have equation dy dt minus y equals e to the power of 3t, how do we use it? We first find integrating factor. And you can use the formulas. For example, here I'm just going to use the formula for integrating factor. So integrating factor, mu of t, look at the coefficient, it's -1, so it's e to the integral of -1 dt, which is -t, right? And again, we set up the constant to 1 because we need just one integrating factor. So normally it's supposed to be plus a constant, which is going to give us a constant in front, but we just need one integrating factor. Looks like it's minus t, right? And then you just can write down your final solution. I'm going to do it too. Y equals 1 over e to the power of -t. Integral, integrating factor, -t, g, e to the power of 3t. Well, I'm going to integrate in t. I'm sorry, I started everything in t, but this t and this t are different t's. I'm not gonna kind of substitute everything into. Sorry, it's supposed to be as here, and as here, right? So e to the power of t, I'm moving this -t in numerator. And here, summing up the powers, I'm going to get e to the power of 2t, and the integral is going to be e to the power of 2t over 2. And I'll need substitutions or just a constant here. So I'm going to get, combining together, e to the power of 3t over 2 plus e to the power of t multiplied by a constant, sorry. Constant is not going to fit over here. So basically that's how we use. If we do have initial condition given here, for example, y, I don't know, of 0 equals 1, then we can find the constant. Let's do it. So we have y of 0, which is going to be here 1 over 2, and here 0 is going to give us 1, so it's plus a constant equals 1. So my constant here, well, because it's 1/2 plus 1/2, it's going to give me 1, so my constant is 1/2. So my final solution here is going to be e to the power of 3t over 2 plus 1 over 2 e to the power of t. So basically, theorem tells me how to find solution and actually gives me the formula. So solution is unique, solution exists, that's a solution. More general theorem is dealing with slightly more general function. So more general theorem. More general theorem for first order equation. This is a linear equation, right? The coefficient here is 1, the coefficient here is p of t, and looks like a polynomial of first degree, right? More general theorem is dealing with equation solved for the first derivative, y of t prime equals f of ty. So if you move everything from this side except derivative to the right side, and it's not necessary must be linear, maybe it's going to have y squared or something like this, but for first order equation looking like this, if f of ty and partial derivative of df dy are continuous, then equation with initial solution y of t0 is going to have a unique solution on interval around the point of initial condition where the functions are continuous. So there is existing and unique solution. This is existence symbol, this is uniqueness symbol solution. In interval is going to be around point t0. I'm going to set it up like t0 minus h, t0 plus h. Somewhere around t0 there is going to be a unique solution, or this initial condition point, where these two function and derivative are continuous. Well, we're not gonna actually check lots of continuity properties or existence just because we don't have time for theory in this class. I'm going to move to section 2.6, and if you are interested, you can read examples from section 2.4. They are interesting examples which are telling when actually there are going to be two solutions, why sometimes solution is not unique, for which functions solution is not unique, and where solution is going to be continuous, where solution is going to exist. But again, that's another lecture to spend if we want to deal with this problem more deeply. Unfortunately, during our first 5 weeks, we are not going to have time to cover everything or all theory in this